Everything you can see tonight, and everything you cannot, was once smaller than the dot at the end of this sentence. Every galaxy, every ocean, every grain of sand on every shore, and every atom resting quietly inside your own hand, was once folded into a point with no width at all. And then, in far less time than it takes a single thought to finish forming, it began to open. Tonight, we are going to follow that opening slowly, from the first thin sliver of a second all the way out to the long, quiet end of things. Before we start, leave a small comment and tell me where in the world you are listening from and what the clock says where you are right now. I like picturing the different rooms these words drift into. Now let your shoulders drop and let the story begin. So let's slow down. There is no hurry tonight, and there is nowhere we need to be. The story we are about to tell took almost 14 billion years to happen, and it is in no rush to be finished. So neither are we. You can let the words wash over you. You do not need to remember any of it. You do not need to follow every turn. If you drift off somewhere in the middle, that is exactly what this is for. And the universe will keep unfolding whether you are awake for it or not. All I am asking is that you get comfortable. Settle your head into whatever is holding it, and let your breathing slow down to match the pace of the telling. We are going to take the single largest story there is, the story of absolutely everything. And we are going to walk through it one calm step at a time, the way you might walk through a quiet house at night, turning on one small lamp after another. Let me start somewhere close to home, somewhere you can actually feel. Hold up your hand in the dark, or just imagine it. Inside that hand, there is iron, the same iron that makes a nail or a key. There is calcium, the same calcium that stiffens a piece of chalk. There is oxygen, carbon, a little phosphorus, a trace of almost everything. And here is the quiet, astonishing fact that we will keep returning to all night. Not one of those atoms was made on Earth. The iron in your blood was forged in the heart of a star that died long before the sun was born. The calcium in your bones was cooked inside a furnace hanging in space, then scattered across the dark when that furnace exploded. You are, quite literally, made of the ruins of older stars. The breath you just took moved atoms that are billions of years old through a body that is only a few decades old. When people say we are made of stardust, they are not being poetic. They are being precise. And the whole point of tonight is to explain, slowly and gently, exactly how that came to be true. Now, here is the question that sits at the center of everything we are about to explore. If you trace your atoms backward, and then trace the stars that made them backward, and then trace the gas those stars formed from backward, where does the line finally stop? Does it stop at all? For most of human history, people assumed the universe simply always was. It had no beginning and would have no end. The stars were eternal furniture, fixed in their places, the same last night as 1,000 years before. It seemed obvious. It seemed safe. And it turned out to be wrong, in one of the most surprising reversals in the history of thought. The universe, it turns out, had a beginning. It has an age. You can count the years since it started, the way you can count the rings in a tree. That number is roughly 13.8 billion. Tonight, we are going to start at year 0 and walk forward. Let's begin at the beginning, in the strangest moment of all. To get to that beginning, though, we have to talk first about the people who found it. Because the story of the universe and the story of how we figured out the universe are braided together. And you cannot really feel the weight of one without the other. So let me take you back, not billions of years yet, but only about 100 to the early part of the 20th century. to a hilltop in California and a quiet priest in Belgium and an idea that almost nobody wanted to believe. Picture a mountain just north of Los Angeles, called Mount Wilson. In the early 1900s, engineers hauled the parts for an enormous telescope up that mountain on mule-drawn wagons, piece by piece, along a narrow trail. When they finished, they had built the largest telescope in the world, with a mirror 100 inches across. They called it the Hooker telescope, after the businessman who paid for the glass. And the man who would spend his nights at the eyepiece was an American astronomer named Edwin Hubble, born in 1889 in Missouri. Hubble was a tall, deliberate, slightly theatrical man who had trained as a lawyer before deciding he would rather study the sky. By the 1920s, he was up on that cold mountain night after night, photographing faint smudges of light that nobody fully understood. Here's the thing about those smudges. For a long time, astronomers argued about what they even were. Some thought they were clouds of gas inside our own galaxy, the Milky Way, which most people assumed was the entire universe. Others suspected they were something far stranger. Hubble settled the argument by measuring the brightness of a particular kind of pulsing star inside one of those smudges, a star whose true brightness could be calculated. He worked out how far away it was. The answer was staggering. The smudge was not a cloud in our galaxy at all. It was another galaxy entirely, an island of hundreds of billions of stars, impossibly far away. In a single stroke, the universe became unimaginably larger than anyone had pictured. The Milky Way was not everything. It was one city in a cosmos of countless cities. Let's slow down for a moment, because what Hubble found next is the real hinge of the whole story. He kept measuring those distant galaxies, and he kept measuring the color of their light. And he noticed something he could not explain away. Almost every galaxy he looked at was running away from us. Not a few of them, nearly all of them. And the farther away a galaxy was, the faster it was fleeing. This is the famous result he published in 1929. The whole sky was, in a sense, draining outward in every direction, like the surface of something being stretched. Now think about this for a second, the way Hubble and others soon did. If everything is flying apart today and you run the film backward, then yesterday everything was a little closer together, and the day before that, closer still. Keep rewinding, far past any human memory, and the galaxies crowd in on one another. Keep going, and the stars themselves have not formed yet, because there is no room. Keep going, and the matter is pressed so tightly and grows so hot that it stops being matter as we know it at all. Run the film all the way back to the very first frame, and everything in existence collapses toward a single, searing, infinitely dense moment. That moment is where the universe begins. And the strange thing is, a man on the other side of the world had already predicted exactly this, 2 years before Hubble's measurements, and almost nobody had listened. His name was Georges Lemaitre. He was Belgian, he was a Catholic priest, and he was also a brilliantly trained physicist and mathematician who had studied at Cambridge and at the Massachusetts Institute of Technology. In 1927, working through the equations that Albert Einstein had recently written down to describe gravity and space, Lemaitre reached a conclusion that the equations seemed to insist upon. The universe was not standing still. It was expanding, and if it was expanding now, then long ago it must have been compressed into what he later called the primeval atom, a single primordial seed from which everything grew. When Lemaitre first explained this idea to Einstein, Einstein reportedly told him that his mathematics was correct, but his physics was abominable. Even Einstein, the man whose own equations were quietly screaming that the universe must move, could not at first stomach the thought that it had a birthday. The eternal, unchanging cosmos was simply too comfortable to give up. But the measurements kept coming, and they kept agreeing with Lemaitre. The universe really was expanding. And slowly, reluctantly, the picture flipped. The cosmos was not eternal furniture after all. It was a process, something that had started and was still going. Decades later, an English astronomer named Fred Hoyle, who personally disliked the whole idea and preferred a universe with no beginning, was talking on a BBC radio program in 1949. Reaching for a vivid phrase to describe this theory he found so distasteful, he called it, dismissively, the Big Bang. The name was meant as a bit of mockery. It stuck anyway, and it has been with us ever since. Even though it is, in almost every way, a misleading name. There was no bang. There was no sound, because there was no air to carry sound. And it did not happen at a point in space that you could fly to, because space itself was part of what was expanding. Keep that in the back of your mind tonight. The beginning was not an explosion in space. It was the beginning of space. All right, let's go there. Let's go to the first moment, and let's go slowly, because it is the strangest territory we will ever cross, and there is no need to rush through the strangeness. We are at time zero, or as close to it as anyone can honestly get. And I have to be honest with you here, because this is where people's eyes start to glaze over. And I would rather slow down than pretend it is simple. There is a very first sliver of time that even the best physics cannot yet describe. It is called the Planck time, and it lasts about 10 to the minus 43 seconds. I know that number means nothing in your body, so let me try to make it mean something. If you took a single second and chopped it into 1,000 pieces, and then took one of those pieces and chopped it into 1,000 again, and you did that chopping 14 times in a row, you would still not have reached the Planck time. It is a duration so short that the word short stops working. During that first unthinkable instant, the universe was so hot and so dense that gravity and the other forces of nature were probably blended into a single thing, and our laws simply dissolve. We do not know what happened there. We only know that the moment ended, and what came next we can begin to follow. So let me set the scene for what came next, the first moment we can actually talk about. The entire universe, everything that would ever become galaxies and stars and oceans and you, is at this point smaller than an atom, and it is unbelievably hot. There are no atoms yet. There are no particles in any familiar sense. There is just a roaring, formless, almost unimaginably energetic something, packed into almost no space at all. And then, in a fraction of a second, that something did the single most consequential thing in all of cosmic history. It grew, not gently, not gradually. It grew in a sudden, violent stretch that physicists call inflation. And once you understand inflation, a great deal of the rest of the night falls into place. So let's take it slowly. Inflation is the idea that somewhere around 10 to the minus 36 seconds after the beginning, the universe doubled in size, and then doubled again, and then again, over and over, dozens of times, in less time than you could ever measure. By the time it finished, around 10 to the minus 32 seconds, a patch smaller than a proton had been stretched larger than a grapefruit. And in cosmic terms, that is an explosion of scale beyond anything that has happened since. Now, here is the question you should be asking, because it is the right one. Why would anyone believe such a wild thing happened? It sounds invented. It sounds like a story told to fill an awkward gap. And the answer is that inflation solves several deep puzzles at once. the way the right key turns several tumblers in a lock at the same time. Let me give you just one of those puzzles, because it is the one you can feel. Look in one direction of the sky, as far as our instruments can see, and then look in the exact opposite direction. The two patches of sky are so far apart that light, the fastest thing there is, has not had time to travel from one to the other across the whole age of the universe. They have never been in contact. They could never have shared heat or settled into agreement with one another. And yet they are, to astonishing precision, the same temperature. The same, as if two kettles on opposite ends of the earth, which had never met and never could, somehow came out at exactly the same warmth. That should not happen, unless long ago those two patches were pressed right up against each other, touching, sharing warmth, before being flung impossibly far apart in an instant. That is what inflation provides. It takes a tiny, smooth, evened-out patch and then stretches it to enormous size so quickly that its smoothness gets locked in across the whole sky. The evenness we see today is a fossil of a closeness that existed before inflation tore it apart. And there is one more gift inflation gave us, and this one matters more than almost anything, because without it, you would not exist, and neither would any star. In that early roaring soup, there were tiny, restless, unavoidable jitters, the kind of minute fluctuations that the deepest layer of physics says can never be perfectly still. Inflation took those microscopic jitters and stretched them too, blowing them up from the scale of the very small to the scale of the very large. Some regions ended up a hair denser than others. A hair. Almost nothing. But that almost nothing was the seed of everything. Wherever the early universe was a touch denser, gravity would later have a little more to pull on, and that is where galaxies would eventually gather. The map of where every galaxy sits today was, in a real sense, sketched in those first fractions of a second, written in faint ripples that inflation enlarged and made permanent. Let that settle for a moment. The arrangement of the stars was decided before the universe was a billionth of a second old. When inflation ended, all the energy that had been driving that mad expansion poured out into a flood of particles, and the universe was suddenly filled with a dense, blisteringly hot fog of matter and radiation. This is the moment most people picture when they hear the words Big Bang, though as we said, it was neither big yet nor a bang. It was hot. Almost beyond meaning, it was hot. And from here, the story changes character. Up to now, everything happened in unthinkable fractions of a second. From here, the universe begins to do something we can finally relate to. It begins to cool down. And nearly everything interesting that follows, every atom, every star, every living thing, happens because the universe is slowly cooling, like a room after a fire has burned low. And because as things cool, they can finally hold their shape. Think about that for a second, because it is a pattern you already know from ordinary life. When water is boiling hot, it is loose and chaotic and will not hold still. Let it cool and it settles. Cool it more and it freezes into something solid and structured, a snowflake with 6 careful arms. The early universe is the same idea written at the largest possible scale. While it is too hot, nothing can stay together. The instant any two particles try to join, the surrounding heat smashes them apart again. Only as the universe expands and cools does the violence drop low enough for things to start sticking. So the entire early history of the cosmos is really a history of falling temperature, and a long series of moments where, one after another, the heat finally drops below the point at which some new kind of structure can survive. We are going to walk through those thresholds, one at a time. The first structures to win that battle were the smallest pieces of ordinary matter. In the first millionth of a second, the universe was a soup of even tinier things, including particles called quarks, drifting free in the heat. Quarks are the components that, in our world, are always locked up inside larger particles. You never find one wandering alone today. But back then it was too hot for them to be bound. So they roamed loose in a kind of primordial plasma. As the temperature fell around that 1/1,000,000th of a second mark, the quarks could finally be captured and held, 3 at a time, inside the particles we call protons and neutrons. Protons and neutrons are the heavy cores that sit at the center of every atom. So at this point, the basic building blocks of the centers of atoms have appeared. The universe now contains protons and neutrons, swimming in a sea of light and other particles, still far too hot for anything larger to form. Now there is a quiet mystery hiding in this part of the story. And I want to pause on it, because it is the reason there is anything at all rather than nothing. In that early heat, matter was not the only thing being made. Its mirror opposite was being made too, a kind of counterpart to ordinary matter that physicists call antimatter. For every ordinary particle, an opposite one. And here is the trouble. When a particle of matter meets its antimatter twin, they do not coexist. They annihilate. They cancel each other completely, vanishing into a flash of pure light. So in those first moments, matter and antimatter were forming and meeting and destroying one another constantly. If they had been made in perfectly equal amounts, they would have annihilated each other entirely. And the universe would have ended up as nothing but light, with no matter left over to build anything. No stars, no planets, no you. The fact that we are here at all means the balance was not perfect. For reasons we still do not fully understand. For every billion particles of antimatter, there were about 1,000,000,001 particles of ordinary matter. A surplus of 1 in 1,000,000,000. When the great annihilation finished, almost everything had canceled out into light. But that tiny leftover, that 1 part in 1,000,000,000, survived. Every atom in every star and every galaxy and every living body is built from that thin remainder. We are, all of us, the small change that the universe failed to spend. Think about that next time you feel insignificant. The entire material world is made from a rounding error that happened to land in our favor. Let's keep cooling. We have passed the first second. By now the universe has protons and neutrons, and it is still hot enough to act like the inside of a star, which means it can do what stars do. It can fuse. When the universe is between roughly 1 and 20 minutes old, the temperature is just right for protons and neutrons to slam together and stick, building the first atomic cores larger than a single proton. Most protons stayed as they were, and a single proton is the core of a hydrogen atom, the lightest and simplest element there is. But some protons and neutrons fused into helium, the next element up, and a tiny trace fused into lithium, the one after that. This window of cosmic cooking lasted only a few minutes. After about 20 minutes, the universe had expanded and cooled too much to keep fusing, and the furnace switched off. So here's what is remarkable. In the first 20 minutes of existence, the universe locked in the recipe that it would carry for billions of years. Roughly 3/4 of all ordinary matter ended up as hydrogen, and almost all the rest as helium, with the faintest sprinkle of lithium. Everything heavier, every atom of carbon and oxygen and iron and gold that would ever exist, did not yet exist. There was no carbon to make life. There was no oxygen to breathe. There was no iron for blood or for nails or for the cores of planets. The early universe was almost embarrassingly simple. Just the 2 lightest elements and very little else. a vast cloud of the plainest possible ingredients. The rich variety of stuff that fills your world had to wait for the stars, and the stars had not been born yet. That is the great task still ahead in our story, and it is worth remembering how bare the cupboard was at the start. And here is the curious thing about this prediction. Long before anyone could check it, a physicist named George Gamow, a Russian-born American with a famously playful sense of humor, worked out in the 1940s that an early hot universe should have produced exactly these proportions of hydrogen and helium. He and his students, including a young researcher named Ralph Alpher, did the calculations. And when astronomers eventually measured the actual amount of helium spread through the oldest, most pristine clouds of gas in space, the number matched the prediction with beautiful precision. About 1/4 of ordinary matter by mass is helium, just as the theory said it should be. That match is one of the quiet pillars holding up the whole idea of a hot beginning. The universe left a receipt, written in the proportions of its lightest elements, and we found it billions of years later. And the numbers added up. Now let's keep moving, because the next stretch of the story is long, and it is dark, and it is one of the most important parts of all. After the first 20 minutes, the cooking is over, but the universe is still far too hot for atoms to actually form. This sounds strange, so let me explain it carefully. We have the cores of atoms, the protons and helium nuclei, and we have electrons, the tiny light particles that, in ordinary matter, circle those cores. You might think they would simply join up right away into finished atoms. But they cannot, not yet, because the universe is still so hot and so full of energetic light that every time an electron tries to settle around a core, a particle of light comes hurtling in and knocks it loose again. The electrons are like nervous birds that keep trying to land on a wire, while a constant wind keeps blowing them off. And because all those electrons are loose, flying free and never settling, the universe is opaque. Light cannot travel in a straight line. Every particle of light, every photon, bounces off a free electron almost the instant it is made, then bounces off another and another, scattering endlessly in every direction. Imagine trying to see across a thick fog. The light from a lamp on the far side never reaches your eye cleanly, because it is scattered by countless tiny droplets along the way. The early universe was exactly like that, a glowing fog with no clear lines of sight, a place where you could not have seen your own hand, because the light would have been knocked sideways before it ever reached you. This foggy era lasted not for minutes or years, but for hundreds of thousands of years. For all that time, the universe was a bright, hot, featureless glow. And it stayed that way, slowly cooling, waiting for one particular temperature to be reached. That temperature arrived about 380,000 years after the beginning. And what happened then changed the universe forever. The cosmos had finally cooled to around 3,000 degrees, which sounds enormously hot. And is, but it was cool enough at last. The light no longer had the energy to keep knocking electrons away from the atomic cores. And so, for the first time, the electrons settled. They slipped into place around the protons and the helium nuclei, and stayed there, and the first complete, stable atoms were formed across the entire universe, all at roughly the same time. Hydrogen atoms, helium atoms, whole, neutral, calm. This event has a slightly misleading name, recombination, even though the electrons and nuclei had never actually been combined before. The name does not matter. What matters is the consequence, and the consequence was sudden and beautiful. The moment the electrons settled into atoms, the fog lifted. There were no more free electrons to scatter the light. Suddenly, the photons could fly. For the first time in the history of the universe, light could travel freely in a straight line across vast distances. And the cosmos, which had been an impenetrable glowing fog, became transparent. Think of standing in a dense mist at dawn, and then watching it thin and clear until the landscape opens up around you. That is what the whole universe did in that era, everywhere at once. And here is the part that should make the hair on your arms stand up gently. That light, the light that was set free 380,000 years after the beginning, is still traveling. It has been crossing space for almost 14 billion years, and it is still arriving right now, tonight, from every direction in the sky. We call that ancient light the cosmic microwave background, and the story of how we found it is one of my favorite accidents in all of science. So let me tell it to you slowly, because it is the kind of story that is nice to fall asleep inside. In the early 1960s, two young radio astronomers were working at Bell Laboratories in Holmdel, New Jersey. Their names were Arno Penzias and Robert Wilson. They had a large, horn-shaped antenna, originally built for bouncing signals off early communication satellites, and they wanted to use it to study faint radio waves from space. To do that, they needed to get rid of every source of noise, every hum and hiss that might contaminate their measurements. They were careful, meticulous people, and they expected to be able to clean their signal down to silence. But no matter what they did, a faint hiss remained, a persistent, low whisper of static that came from every direction in the sky, day and night, summer and winter, never changing, never fading. They checked their equipment over and over. They suspected the antenna itself. They found that a pair of pigeons had been roosting inside the horn and leaving droppings, which Penzias delicately described as a white dielectric material. And they cleaned it all out. And they even removed the pigeons, and still the hiss remained. They were honest scientists, and they were stuck. They had found something they could not explain, and they did not know that what they were hearing was the oldest sound in existence. The faint, cooled-down echo of the universe becoming transparent. The light released at recombination, stretched by billions of years of cosmic expansion, until it had slipped from a brilliant glow down into the gentle range of radio waves. Now here is where two stories come together. And it is the kind of coincidence that makes the history of science feel like a novel. Just a short drive away, at Princeton University, a team of physicists led by Robert Dicke had been working out, on paper, that an early hot universe should have left behind exactly this kind of leftover radiation. A faint afterglow, filling all of space, cooled to just a few degrees above the coldest possible temperature. They had even started building an antenna to look for it. They were close. And before they could finish, a phone call connected the two groups. Penzias and Wilson described their stubborn hiss. Dicke hung up the phone, turned to his colleagues, and said, in effect, "We have been scooped." The faint static that two engineers could not get rid of was the prize that the theorists had been about to chase. The afterglow of the beginning had been found by accident, by people who were not even looking for it, and who at first just wanted it to go away. Penzias and Wilson received the Nobel Prize for it years later, in 1978. And remember George Gamow and Ralph Alpher, the men who had calculated the early helium. Along with another colleague, Robert Herman, they had actually predicted, back in the late 1940s, that such an afterglow should exist, and had even estimated roughly how cold it would have become. Their prediction had been largely forgotten, set aside, unfashionable. The universe had quietly proved them right, and almost nobody remembered to give them credit at first. There is a lesson in that somewhere about how truth can sit waiting and ignored for years before the world catches up to it. But the truth was not going anywhere. It was filling the sky the whole time. Since then, we have studied that ancient light with extraordinary care. Satellites were sent above the atmosphere to map it across the entire sky. One was called COBE, launched in 1989, led by scientists including John Mather and George Smoot, who later shared a Nobel Prize for the work. Then came another satellite called WMAP, and then an even sharper European observatory called a Planck. What they found, when they mapped that ancient glow in fine detail, was breathtaking in its quietness. The afterglow is almost perfectly smooth, the same temperature in every direction, just under 3 degrees above absolute zero, the coldest temperature there is. But it is not perfectly smooth. Across that smoothness, there are faint ripples, spots a tiny bit warmer and a tiny bit cooler than the average, differences of only 100,000th of a degree. And those ripples, those almost invisible variations, are the very same density fluctuations we talked about earlier, the ones inflation stretched out in the first instant. We are looking at the seeds of every galaxy, photographed when the universe was 380,000 years old. The map of that ancient light is, in a real sense, a baby picture of everything. It is the oldest image that exists, and it is hanging in the sky above your roof right now, glowing too faintly and too coldly for your eyes to see. Let's pause here and breathe. We have come a long way already, from a point smaller than an atom, through inflation, through the cooling, through the first nuclei and the first atoms, to the moment the fog lifted and the light went free. And yet, for all of that drama, the universe at this point is still a remarkably dull place to look at. It is a vast, dim, expanding sea of hydrogen and helium gas, slowly cooling in the dark. There are no stars. There is no light being made anymore, only the old afterglow fading. If you could have floated through the universe at this age, you would have seen nothing at all, just blackness in every direction, a warm darkness slowly going cold. Astronomers, with a kind of poetry that scientists pretend they do not have, call this stretch of time the cosmic dark ages. And the dark ages lasted a long time, tens of millions of years, maybe 100 million, with nothing to see, while gravity did its slow and patient work behind the curtain. Because gravity was working, this is the part to hold on to as you drift. Remember those faint ripples, the spots that were a hair denser than their surroundings. In the dark, with all the time in the world, those slightly denser regions began to pull. Gravity is patient and relentless. Wherever there was a little extra matter, it pulled in a little more, which gave it more pull, which drew in more still. The denser places grew denser, slowly, over millions of years, gathering the surrounding gas the way a slow drain gathers water, the way dust collects in the corners of a quiet room. The smooth sea of gas was breaking, imperceptibly, into clumps and threads and vast gathering pools. Nothing was glowing yet, but the architecture of everything was being drawn in the dark. And at the centers of the densest pools, the gas was getting thicker and warmer and more crushed, pressing down on itself under its own growing weight, building toward a moment. And then, somewhere in that darkness, perhaps 100 or 200 million years after the beginning, in the densest heart of one of those gathering clouds, the pressure and the heat at the center crossed a threshold, and something switched on. The hydrogen at the core was squeezed so hard and grew so hot that it began to fuse. Protons forced together into helium, the same reaction that had happened in the first 3 minutes of the universe, but this time concentrated and sustained in one small, brilliant point. Energy poured out. Light blazed. For the first time since the fog had lifted, the universe was making new light of its own. The first star had been born, and after 100 million years of darkness, the long night of the cosmos began, at last, to fill with scattered points of fire. Let's spend some time with those first stars, because they are strange, and because everything you are made of began inside stars like them. The very first stars were nothing like our gentle sun. They were built from pure hydrogen and helium, the only ingredients the early universe had, and without heavier elements to help them shed heat, they could grow to monstrous sizes, dozens or even hundreds of times the mass of the sun. They burned with a fierce, blue-white intensity, and they did not last long. This is one of the quiet rules of the cosmos, and it feels almost unfair. The biggest, brightest stars burn through their fuel the fastest and die the youngest. A small, modest star can glow steadily for tens of billions of years. A giant star may live only a few million. The first stars were giants, and so they lived fast and died young, blazing for a cosmic instant and then going out. But before we follow them to their deaths, let me explain what a star actually is. Because we say the word so easily, and the truth of it is more wonderful than the word suggests. A star is, at its heart, a balancing act between two opposing forces, held in tension for millions or billions of years. On one side there is gravity, the weight of all that gas pulling relentlessly inward, trying to crush the star down to a point. On the other side, there is the heat and pressure generated by fusion at the core, pushing relentlessly outward, trying to blow the star apart. A star is what happens when those two forces find a standoff, a long and stable truce, neither winning, each holding the other at bay. The inward crush of gravity heats the core enough to drive fusion, and the outward push of fusion holds back the crush of gravity. As long as there is fuel to burn, the truce holds, and the star shines steadily, a quiet equilibrium hanging in the dark. The day the fuel runs low is the day the truce breaks, and that is when the most dramatic events in the universe begin. Now, here's something I want you to sit with, because it took humanity a surprisingly long time to figure out, and the person who figured it out was nearly talked out of it. For centuries, nobody knew what the stars were made of. They seemed utterly beyond reach. How could you ever know the composition of something you could never touch, never visit, never bring into a laboratory? The French philosopher Auguste Comte, writing in the 1830s, used the chemistry of the stars as his example of something humans could never possibly know, and he was wrong almost immediately because of a discovery about light. When you pass sunlight through a prism, it spreads into a rainbow, a band of colors from red to violet. That much had been known for a long time. But in the early 1800s, a German optician named Joseph von Fraunhofer, who made some of the finest glass and instruments of his age, looked very carefully at that spread-out band of sunlight, and he noticed something that earlier observers had missed. The rainbow was not perfectly smooth. It was crossed by hundreds of fine, dark lines, narrow gaps where particular colors were missing, as if someone had drawn thin pencil marks across the spectrum at precise places. Fraunhofer carefully measured the positions of these dark lines, hundreds of them, without yet knowing what they meant. He had stumbled onto a code written in the missing colors of sunlight, a code that would eventually reveal the chemistry of the stars. The meaning of those dark lines became clear over the following decades. It turned out that each chemical element, when it is hot, absorbs and emits light at its own particular set of colors, as distinctive as a fingerprint. Sodium has its colors. Hydrogen has its colors. Iron has its own crowded signature of lines. When the light from inside a star passes outward through the cooler gas of the star's own atmosphere, the elements in that gas drink up their particular colors, leaving dark gaps in the rainbow exactly where Fraunhofer had seen them. So those missing colors were not flaws. They were a message. Read the pattern of dark lines in a star's light, and you can read off which elements the star contains without ever leaving the Earth. The thing Comte had declared forever unknowable became, within a few decades, routine. We learned to taste the chemistry of the stars from the colors they failed to send us. There is a lovely detail tucked inside this story. In 1868, astronomers studying the light of the sun during an eclipse found a set of dark lines that matched no element known on Earth. A brand new fingerprint. They concluded there must be an element present in the sun that nobody had ever found on our planet. And they named it after the Greek word for the sun, helios. They called it helium. For more than 20 years, helium was known only as a substance in the sun, an element discovered in the sky before it was ever found in the ground. It was only later isolated here on Earth. The second most common element in the entire universe, the very stuff cooked in the first 3 minutes of creation, was first detected as a whisper of missing color in sunlight. Two astronomers, the Frenchman Jules Janssen and the Englishman Norman Lockyer, are remembered for that discovery, made on opposite sides of the world within months of each other. And then comes the part that should genuinely move you, because it concerns a young woman who was told she was wrong and turned out to be profoundly right. In 1925, a British-born astronomer named Cecilia Payne, working at Harvard, completed a doctoral thesis that is now considered one of the most brilliant ever written in astronomy. By carefully analyzing the fingerprints of light from many stars, she reached a startling conclusion. The stars were not made of roughly the same stuff as the Earth, as nearly everyone assumed. They were overwhelmingly made of hydrogen, the lightest and simplest element, with helium next, and everything else a tiny remainder. When she showed her work to a senior astronomer of the day, he pressed her to soften the claim, to call it spurious, because it contradicted what everyone believed. So she did, reluctantly, in her thesis. And within a few years, the evidence became undeniable, and it was clear that she had been right all along. The universe runs on hydrogen and helium, just as she had found. It is hard not to feel a little ache at how nearly that truth was buried out of politeness. But the stars did not care about politeness. They were hydrogen, and she had read them correctly. So now we understand what the first stars were doing, deep in their cores, in those first hundreds of millions of years. They were taking hydrogen, the simple leftover of the beginning, and fusing it into helium, releasing light. And when a massive star starts to run low on hydrogen in its core, something important happens. Something that will eventually fill the universe with everything heavier. The core contracts and heats further, and at the new, higher temperature, it begins to fuse helium into still heavier elements, into carbon, the backbone of all life, and oxygen, the element you are breathing right now. A truly massive star does not stop there. It builds layer by layer, like the rings of an onion, fusing carbon into neon, neon into oxygen and magnesium, on and on, each stage hotter and faster than the last, manufacturing heavier and heavier elements in its searing heart. This is the great forge of the cosmos. The variety of matter that the early universe lacked, all the richer elements your world is built from, was being assembled slowly and then quickly inside the cores of dying stars. But there is a limit to this building, and the limit is the key to one of the most violent and creative events in the universe. So let me walk you up to it gently. As a massive star fuses heavier and heavier elements, it eventually reaches iron. And iron is special in a quiet, fatal way. Up until iron, fusing lighter elements into heavier ones releases energy, which is what keeps the star's outward push going, what keeps the truce with gravity alive. But iron is the end of the road. Fusing iron into anything heavier does not release energy. It absorbs it. So when a star's core finally turns to iron, the furnace can give nothing more. The outward push stops, suddenly and completely, like a fire that has run out of fuel in a single instant. And in that instant, gravity, which has been held off for millions of years, finally wins. What happens next takes less than a second, and it is almost beyond comprehension. With no outward push to hold it up, the iron core, an object often larger than the Earth, collapses inward at a quarter of the speed of light. It crushes down in a heartbeat, from the size of a planet to the size of a city, and the falling material slams into the impossibly dense core and rebounds, blasting outward in a shockwave of unimaginable force. The outer layers of the star, all those carefully built shells of carbon and oxygen and silicon and iron, are blown off into space in a titanic explosion. We call it a supernova. For a few weeks, a single dying star can outshine an entire galaxy of 100 billion ordinary stars. A single point of light blazing brighter than all its neighbors combined. And here is the gift hidden inside that violence. The reason it matters to you personally. In the searing heat and crushing pressure of the explosion itself, elements heavier than iron are forged. Elements that no ordinary star could ever make in its quiet life. The silver and gold, the lead, the elements that fill the periodic table beyond iron, are born in the deaths of stars and in the collisions of their dense remnants. And then the explosion scatters everything, all of it, every element the star ever made, out into the surrounding space. The carbon, the oxygen, the iron, the gold, all of it, flung outward into the great clouds of gas drifting between the stars, enriching that gas, salting the plain hydrogen and helium with the full richness of heavier matter for the very first time. So picture the universe now, perhaps 1 billion years after the beginning. The first generation of giant stars has lived and died. Their explosions have seeded the surrounding gas with carbon and oxygen and iron and all the rest. And out of that enriched gas, new stars begin to form. Stars that, unlike the first ones, are born already containing the heavier elements. And around some of those new stars, the heavier elements can clump together into something the universe has never had before. They can clump into rock and metal and dust. They can form planets. The stage is being set, slowly, for worlds. But none of it, not a single planet, not a single living cell, could exist if those first giant stars had not lived and died and given away everything they made. Every time you look at a gold ring, you are looking at the relic of a dead star, or the collision of 2 dead stars, billions of years ago. Every breath of oxygen was once locked inside a star that exploded. We did not just come from the stars in some vague way. We came from their specific, individual deaths. Let's pull back now and watch this happening on the grandest scale. Because while individual stars were living and dying, something larger was assembling around them. The stars were not scattered evenly. They were gathering by the hundreds of billions into vast, spinning islands of light. They were forming galaxies. Remember those slightly denser regions of the early universe, the seeds that gravity had been working on in the dark. Where the gas pooled most thickly, not just single stars, but whole swarms of stars lit up together. And gravity drew those swarms into structures, into the great pinwheels and ellipses and clouds of stars we see today. Our own galaxy, the Milky Way, began assembling in this era, gathering its stars over billions of years, building itself up partly by drawing in gas and partly by swallowing smaller galaxies whole, a slow and gentle cannibalism that is still going on today. And here is where the universe handed us a deep and unsettling mystery. One we have still not solved, so let me lay it out for you plainly, the way it first appeared. In the 1970s, an American astronomer named Vera Rubin was carefully measuring how galaxies spin. Now, you would expect a galaxy to behave a little like the solar system, where the planets close to the sun orbit quickly, and the distant planets orbit slowly, because the sun's gravity weakens with distance. The stars far out at the edge of a galaxy should, by the same logic, move more slowly than the stars near the crowded center. That is what everyone expected Rubin to find. That is what the visible matter, all those stars and clouds of gas, said should happen. But it is not what she found. She found that the stars at the far edges of galaxies were moving just as fast as the stars further in. They were orbiting so quickly that, by all the rules of gravity, they should have been flung off into space long ago. The visible matter in the galaxy simply did not have enough gravity to hold those fast-moving outer stars in place. And yet they were held. Something was gripping them. Something with a great deal of gravity, something we could not see, something that gave off no light at all. Rubin had found the fingerprints of a vast, invisible presence wrapped around every galaxy, far outweighing all the visible stars, and we still, to this day, do not know what it is made of. We call it dark matter, which is really just an honest admission of our ignorance dressed up in a name. It is not dark in the sense of being black. It is dark in the sense that it does not interact with light at all, so we cannot see it, only feel its pull. Let's slow right down for a moment, because dark matter is genuinely strange, and it deserves a calm thought rather than a rushed one. Imagine a city at night, seen from very high up. You can see the street lights, the lit windows, the moving headlights, a glittering web of light spread across the dark. Now imagine that the actual buildings, the roads, the ground itself, all of it, is completely invisible to you. You can only see the lights. You would have to work out the shape of the entire city just from how the lights were arranged and how they moved. That is roughly our situation with the cosmos. The stars and galaxies are the lights. But the great invisible structure that holds them, that shaped where they gathered, that scaffolding of dark matter, makes up far more of the universe than everything we can see. The luminous part, all the stars and gas and all the galaxies, is only a small fraction of what is really there. We live in a universe whose major furniture is invisible to us, and we have been quietly piecing together its outline from the way the lights are arranged. So the dark matter was there from early on, gathering first, forming an unseen web of dense regions and connecting filaments. And the ordinary matter, the gas, fell into the wells that the dark matter had already dug. The galaxies lit up inside those wells like lamps placed inside an invisible scaffold. And that is the structure of the universe today, on the very largest scale. Galaxies are not scattered randomly. They are strung along immense filaments and gathered at the junctions where filaments meet, with vast, nearly empty voids between them. If you could see the whole universe at once, dimmed down and sped up, it would look strangely organic, like a network of threads. or the branching structure inside a living thing, a cosmic web spun in the dark across billions of light years. And all of it grew from those faint ripples that inflation stretched in the first instant. The largest structures in existence are the grown-up form of the smallest jitters at the very beginning. The cosmos remembered its first breath and built galaxies out of it. Now let's bring this enormous story home, all the way home, to a particular cloud of gas in a particular corner of one particular galaxy, our Milky Way, about 4.5 billion years ago. By this time, the universe is already more than 9 billion years old. Generations of stars have already lived and died in our galaxy, enriching the gas with carbon and oxygen and iron and gold. And in one ordinary region of one ordinary spiral arm, a great cloud of this enriched gas and dust is drifting, cold and dark and quiet, doing nothing in particular for a very long time. And then something disturbs it. Perhaps the shock wave from a nearby supernova, the death of yet another star, ripples through the cloud and compresses it. Whatever the trigger, the cloud begins to collapse under its own gravity, gathering inward, growing denser at the center, the way a slow whirlpool draws everything toward its middle. As the cloud collapsed, it began to spin faster, and to flatten the way any spinning, collapsing thing tends to flatten into a disk. At the center, where the most material gathered and the pressure climbed highest, the temperature rose and rose, until, once again, the old miracle happened. Hydrogen at the core was crushed hot enough to fuse, and a new star switched on. Our star. The Sun. It was not the first star. Not by billions of years. It was a latecomer. An ordinary yellow star of middling size, born into a universe that was already ancient. But it was ours. And around it, in the flattened disk of leftover gas and dust, the heavier elements that earlier stars had made began to stick together. Grain by grain, pebble by pebble, building up over millions of years into rocks and then into worlds. The inner worlds, close to the heat, formed from rock and metal. Mercury, Venus, Earth, Mars. The outer regions, cold enough for ice and gas to gather in huge amounts, built the giant planets, Jupiter and Saturn and the rest. And on the third small rock from that ordinary star, something would eventually happen that, as far as we yet know, happened nowhere else. Here's the thing about Earth that I find quietly staggering, and I want to say it slowly. Every atom in this planet, every atom in the rock beneath you, and the water in the oceans, and the air you breathe, every atom except the original hydrogen, was made inside a star that died before the sun existed. The Earth is, in the most literal sense, an assembly of stellar ash, gathered together and shaped by gravity into a world. The iron at the core of the planet, the iron that gives us our magnetic field and shields us from the solar wind, is dead star iron. The carbon in every living thing is dead star carbon. The oxygen in the seas, the silicon in the sand, the gold in the ground, all of it cooked in stars and scattered by their deaths, then gathered up again into a single new world. You are not living on top of the universe, separate from it. You are living on a piece of the universe that has been reassembled into a planet, and a small part of that planet has astonishingly woken up and started asking where it came from. That is what you are doing right now, lying there in the dark. You are a way for the universe to wonder about itself. And on that third rock, somehow, within perhaps a few 100 million years of the planet's formation, in the warm chemistry of the early oceans, matter did something it had never done before. It began to copy itself. Some arrangement of those star-forged atoms, those carbons and oxygens and the rest, fell into a pattern that could make rough copies of itself from the materials around it. We do not yet fully understand how that first step happened, and it remains one of the great open questions. But once it began, it never stopped. Those self-copying patterns competed and changed and grew more intricate over billions of years, from single cells to vast forests and swimming things and walking things. And eventually, on one branch of that immense and ancient tree, to a creature that could look up at the night sky and feel that it recognized something there. The stardust had organized itself into something that could remember the stars. It took a very long time. If you compressed the whole history of the universe into a single year, with the beginning on the first second of January, then the Sun and Earth would not form until late August or early September. The first simple life would appear soon after. But for most of that compressed year, life would remain microscopic and quiet. The dinosaurs would not appear until the very last week of December, and they would be gone a few days later. And all of recorded human history, every empire and every invention and every person who ever lived and wrote anything down, would fit into the last few seconds before midnight on the 31st of December. We are very, very new. The light from the cosmic dark ages has been traveling for almost the entire year. We arrived in the final breath of it. And yet, here we are, having figured out a remarkable amount of the story in just those last few seconds, which is either humbling or magnificent, depending on how you hold it. Now I want to turn us back outward, away from our small, warm world, and toward the largest question of all, the one the whole night has been circling. The universe began by expanding. Hubble showed it was still expanding. So the obvious question, the one astronomers have asked for nearly a century, is simple. What happens in the end? Does the expansion go on forever, or does it eventually stop? For a long time, the most natural guess was that gravity would slowly win. All the matter in the universe pulls on all the other matter. So surely, people reasoned, the expansion that began at the beginning must be gradually slowing down, like a ball thrown into the air, rising but losing speed, decelerating under the steady pull of all that gravity. The only question seemed to be whether there was enough matter to eventually halt the expansion and pull everything back together, or whether it would coast outward forever, slowing but never quite stopping. To find out, in the 1990s, two competing teams of astronomers set out to measure exactly how much the expansion was slowing down. They used a particular kind of exploding star, a special type of supernova that always blazes with very nearly the same true brightness, which makes it a kind of standard candle. If you know how bright something truly is, and you measure how bright it appears, you can work out how far away it is. So these teams went hunting for these standard exploding stars in very distant galaxies, looking billions of years into the past, trying to measure how the expansion rate had changed over cosmic time. One team was led by Saul Perlmutter. The other included Brian Schmidt and Adam Rees. They expected to measure the gentle slowing of the cosmos. They were, in a sense, just trying to pin down the number. And then, around 1998, both teams independently found something that made no sense. Something that several of them initially assumed was a mistake in their own work. The distant supernovae were fainter than they should have been. Fainter meant farther. Farther than they would be if the expansion had simply been coasting or slowing all this time. The only way to explain it was almost too strange to say out loud. The expansion of the universe was not slowing down at all. It was speeding up. For the last several billion years, the universe has been expanding faster and faster, as if something were pushing it apart, overpowering the inward pull of all the gravity of all the matter there is. The ball thrown into the air was not falling back. It was rising faster. Both teams checked and rechecked, terrified of being wrong about something so large, and the answer held. The cosmos was accelerating. Whatever is causing that acceleration, we have given it a name. And the name, once again, is mostly a confession of ignorance. We call it dark energy. It seems to be a kind of pressure woven into the fabric of empty space itself, a faint push that exists in every cubic inch of vacuum, so weak that you would never notice it in a room or even in a solar system, but so pervasive, filling all the unimaginable emptiness between the galaxies, that across the vastness of the cosmos, it adds up to the dominant force in the universe. And here is the figure that humbles every physicist who says it. When you add it all up, the ordinary matter that makes you and the Earth and the stars, all the atoms of everything we have ever seen or touched, comes to only about 5% of the universe. Around a quarter is the invisible dark matter. And the rest, roughly 2/3 of everything, is this dark energy we cannot explain. We have spent this whole night telling the story of the 5%. The other 95% remains, even now, a mystery glowing at the edge of our understanding. The 3 astronomers who found the acceleration, Perlmutter, Schmidt, and Rees, shared the Nobel Prize for it in 2011, for discovering that the universe was running away from itself faster and faster, for a reason no one yet knows. So now, at last, we can ask the question this whole story has been quietly leading toward. If the expansion is accelerating, if the galaxies are flying apart faster and faster, then what does the far, far future look like? And this is where the story turns very quiet and very long and strangely peaceful, which makes it, I think, a fitting place to be drifting towards sleep. Because the end of the universe, as far as we can tell, is not a bang at all. It is a slow, gentle, almost tender fading. It is the longest, softest good night there is. Let me walk you forward, slowly, through the deep future. Right now we live in what astronomers call the age of stars, the bright era, when the sky is full of suns being born and shining and dying. But star formation cannot go on forever, because it depends on having gas to make new stars from, and the universe has a finite supply. Every star that forms locks up some of that gas, and much of it never returns. So the rate of new star birth, which already peaked billions of years ago, will keep declining. Far in the future, perhaps 100 trillion years from now, the last clouds of star-forming gas will be exhausted. The last new star will ignite. And after that, no new stars will ever be born again. The universe will be lit only by the stars that already exist, slowly burning down, one by one, like candles left to gutter in an empty hall. The longest-lived stars are not the giants, but the smallest, dimmest ones. The little red stars that sip their fuel so slowly they can shine for trillions of years. So they will be the last to go. Faint red embers scattered across an increasingly empty and dark cosmos, while the accelerating expansion carries the other galaxies so far away that eventually they slip beyond the reach of sight entirely. There will come a time, in that distant future, when any creatures living near one of those last red stars would look up and see nothing beyond their own galaxy at all, the rest having receded past the horizon of the visible, leaving them alone in an apparently empty void, with no way to ever know that the great cosmic story had ever happened. We are lucky, in a way, to be alive now, while the evidence is still in the sky, while the light of the beginning still reaches us. We are living in the readable chapter of the book, before the pages drift too far apart to be read. After the last stars burn out, the universe enters a long twilight that astronomers sometimes call the degenerate era, and the names of its inhabitants are themselves a kind of poetry. The stars do not simply vanish when their fuel runs out. They leave behind remnants, the cooling cores of what they once were. A star like our sun, when it dies, will not explode. It will gently puff off its outer layers and leave behind a small, dense, glowing ember called a white dwarf, an object about the size of the Earth, but containing much of the mass of a star, so heavy that a spoonful of it would weigh tons. And a white dwarf, having no more fuel to burn, simply cools, slowly. Over unimaginable spans of time, it radiates its leftover heat away into the dark and fades, from white to yellow to red, dimmer and dimmer until at last it becomes cold and black and silent, a dead cinder drifting in space. Our own sun is destined for this fate, billions of years from now, after first swelling into a red giant large enough to swallow the inner planets. The Earth's story, one way or another, ends in that swelling. The more massive stars leave behind even stranger remnants. A star several times heavier than the sun ends its life leaving a neutron star, an object so dense that the entire mass of a star is crushed into a sphere only a dozen miles across, where a single sugar cube of material would weigh as much as a mountain. And the most massive stars of all leave behind the strangest objects in the universe, the black holes, regions where matter has collapsed so completely that gravity overwhelms everything, even light, so that nothing which falls in can ever climb back out. For a very long stretch of the deep future, the universe will be a quiet museum of these remnants. White dwarfs slowly cooling, neutron stars spinning down, black holes drifting in the dark. The bright era of stars will be a distant memory, and the cosmos will be lit only by the last dim glow of cooling embers, growing fainter century after century, eon after eon, for a span of time so long that our usual numbers stop meaning anything. And then even those embers go out, and we enter the age of the black holes, the longest era of all, by an almost incomprehensible margin. By now, perhaps after spans of time written with 100 zeros, the white dwarfs have gone cold and dark, the neutron stars have stilled, and the matter of dead stars has, through processes we can barely sketch, mostly given way. What remains, scattered across an unthinkably vast and empty space, are the black holes, the last great structures standing, having grown enormous by swallowing whatever drifted near them over the long ages. The universe in this era is darker and emptier than anything we can really picture. A near-perfect void, cold beyond cold, with these silent black wells of gravity floating impossibly far apart, each one alone in its own patch of nothing. But here's something that genuinely astonished physicists when they first worked it out, and it is the gentle ending to even the black holes. So let me tell it to you softly. For most of history, people assumed a black hole was truly forever, a perfect trap from which nothing could ever escape. And then, in the 1970s, a young English physicist named Stephen Hawking, working through the strange rules that govern the very small, showed that this is not quite true. Even black holes, he found, very slowly leak. Through a subtle process at the very edge of a black hole, where the deepest physics of empty space comes into play, a black hole gives off the faintest possible trickle of radiation, and in doing so loses, over time, a tiny sliver of itself. The leak is unimaginably slow. For any normal black hole, it would take far longer than the present age of the universe to lose even a noticeable amount. But the deep future has all the time there could ever be. And given enough time, even the largest black hole will slowly evaporate away, shrinking over spans of time so vast that the numbers become almost meaningless, until at last, in a final faint flicker, it is gone. And so we arrive at the end, the true far end, what some have called the dark era, the long quiet that comes after even the black holes have faded. The universe by then is unrecognizable. There are no stars. There are no planets. There are no black holes. There is no light being made anywhere. There is only an immense, cold, thinning haze of the last leftover particles, drifting ever farther apart in an ever-expanding darkness, growing colder and emptier and more silent, approaching but never quite reaching the absolute zero of temperature, the stillest possible state. Nothing happens. Nothing changes. There is no event to mark time by, no birth, no death, no light, no warmth, only an endless, expanding, deepening quiet, going on as far as we can tell forever. This is the fate that physics, as we currently understand it, points toward. Not a crash, not a fire. Just a slow and final settling into stillness, the universe exhaling one last time and then resting. Now, I know that might sound bleak, lying there in the dark, but I want you to notice something about it, because I find it strangely consoling, and I hope you will too. That ending is unimaginably far away. The numbers are so large that the entire history we have told tonight, all 13.8 billion years of it, from the first instant to this very moment, is less than the blink of an eye compared to the ages still to come. We are not living near the end. We are living at the very, very beginning. The universe is young. The stars are still shining. New ones are still being born. The light of the cosmic dawn still reaches our telescopes. We happen to be alive in the bright morning of everything, in the brief, luminous chapter when there are stars to see, and creatures to see them. And that is not a small thing to be. It may, in fact, be the rarest and most precious window the universe will ever have. And you are inside it, right now, breathing. Let me come back from the far future now. Back to the present, back toward your quiet room. And let me share one more idea before we begin to wind down, because it is one of the most beautiful facts in all of astronomy, and it changes how you see the night sky forever. Here it is. When you look up at the stars, you are not seeing the present. You are looking into the past. Light travels fast, faster than anything. But it does not travel instantly. It takes time to cross space. The light from the sun takes about 8 minutes to reach us, which means you never see the sun as it is, only as it was 8 minutes ago. The light from the next nearest star takes more than 4 years to arrive. So you see that star as it was 4 years in the past. And the light from distant galaxies has been traveling for millions or billions of years before it reaches your eye. So think about this for a second, gently, as you lie there. Every time you look at the night sky, you are looking at a collage of different moments in history, all arriving at once. That star over here as it was a decade ago. That one as it was 1,000 years ago. That faint smudge of a galaxy as it was when the Earth was barely formed. The sky is not a snapshot of now. It is a layered record of the past. The deeper you look, the further back you see. To look out into space is to look back in time. And this is not a poetic flourish. It is the literal mechanism that lets us study the early universe at all. When astronomers want to see what the cosmos looked like billions of years ago, they do not need a time machine. They simply look very, very far away, because the most distant light is also the oldest light, set out on its journey when the universe was young. This is exactly what our newest great telescope was built to do. The James Webb Space Telescope, launched at the very end of 2021 and parked 1 million miles from Earth, was designed to catch the faintest, most stretched out, most ancient light there is. The light from the very first galaxies that formed after the cosmic dark ages. It looks so far away that it sees the universe as it was more than 13 billion years ago, as those first structures were lighting up. We built an instrument capable of seeing nearly to the beginning, simply by looking far enough into the distance, and therefore far enough into the past. The baby pictures of the cosmos are still out there, still arriving, and we have finally built eyes sharp enough and patient enough to catch them. Somewhere above you right now, that telescope is quietly gathering the oldest light in the universe, photon by photon, the way you might gather rainwater, one slow drop at a time. And here's what's worth holding on to about all of this. Everything we have talked about tonight, the inflation in the first instant, the cooling, the first atoms, the afterglow in the sky, the forging of elements in dying stars, the invisible scaffolding of dark matter, the strange acceleration of dark energy, the long, quiet end. None of it was handed to us. No one was there at the beginning to write it down. Every piece of this story was painstakingly assembled by people, ordinary people with extraordinary patience, sitting at telescopes on cold mountaintops, scribbling equations at kitchen tables, staring at faint smudges on photographic plates, arguing with one another, being wrong and then being right over many generations. The priest Georges Lemaitre, working out that the universe must have had a beginning. Edwin Hubble, measuring galaxies fleeing into the dark. Cecilia Payne, reading the hydrogen in starlight and being told to doubt herself. George Gamow and Ralph Alpher, predicting an afterglow no one had seen. Arno Penzias and Robert Wilson, mistaking the oldest light in the universe for noise in their antenna. Vera Rubin, finding the invisible matter that holds the galaxies together. Stephen Hawking, showing that even black holes one day fade. They built this story the way a cathedral is built, one careful stone at a time, most of them never living to see it finished. And the most astonishing part, the part I keep coming back to, is that the universe turned out to be understandable at all. There was no guarantee of that. It did not have to be the case that a curious creature living for a few decades on a small wet rock orbiting an ordinary star could look up and measure and reason and actually piece together the history of all existence back to its first fraction of a second. The cosmos could have been forever beyond our reach. Instead, somehow, it left clues everywhere, in the colors of starlight, in the proportions of the elements, in the faint glow filling the sky, in the way galaxies spin. It left a story written across itself, and it produced, on at least one small world, a creature patient enough to read it. You are part of how the universe came to know itself. That is not a small inheritance to carry into sleep. So let's gather it all together now, slowly, the way you might fold a blanket at the end of a long day. We began with everything pressed into a point smaller than an atom. We watched it unfold in the first instant, faster than thought. We felt it cool, and we watched the first particles form, and then the first atoms, 380,000 years in, when the fog lifted and the light went free. That same light still falling softly on your roof tonight. We sat through the long, dark ages, while gravity quietly drew the gas into clumps. We watched the first stars ignite and live and die, scattering the elements that would become everything, including you. We saw galaxies gather along an invisible web. We watched our own sun and earth condense from the ashes of older stars, and we saw a small part of that stardust wake up and begin to wonder. And we followed the story all the way out to the long, quiet end, so far away that we are still in the bright and early morning of it all. Let me linger here a little longer, in no hurry at all, on the sheer scale of the thing. Because there is something restful about vastness when you let it be restful rather than frightening. Our galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars. That is one galaxy. And the observable universe contains, by careful estimates, something like 2 trillion galaxies, each one a city of billions of suns. The numbers are so large that they stop being numbers and become a kind of texture, a softness, the way the grains of sand on a beach stop being countable and just become the beach. There are more stars in the observable universe than there are grains of sand on every shore and in every desert on the earth. Many, many more. And around a great many of those stars, we now know there are planets, because in the last few decades, we have learned to detect them. Thousands and thousands of worlds orbiting other suns, some of them rocky, some of them the right distance from their star for liquid water. Some of them not so different, perhaps, from the small blue world you are lying on right now. There is no need to feel small in the face of that, though people often expect to. You might just as easily feel held. You are not separate from this immensity, standing outside it and being dwarfed by it. You are made of it. The same handful of elements, forged in the same kind of stellar furnaces, assembled by the same patient gravity, arranged for a little while into the particular shape that is you. The atoms in your hand have been, at various times over the last 14 billion years, part of the original hot soup of the beginning, part of clouds of gas drifting in the dark, part of the searing core of a star, part of the debris of a supernova, part of the rock of the early Earth, part of the ocean, part of countless living things before you. And now, for a few decades, part of you. And when your particular arrangement ends, as all arrangements do, those atoms will go on, into the soil, into the air, into other living things, into the slow recycling that the universe has been doing all along. Nothing is wasted. Nothing is truly lost. It is only ever rearranged. That, in the end, may be the deepest pattern of the whole story, and it is a gentle one to fall asleep on. The universe is a great recycler. The first stars made the elements and then died and gave them away. Out of their scattered ashes, new stars formed and made more elements and died and gave those away in turn. Our sun is built from the leftovers of earlier suns. The earth is built from their ash. You are built from the ash of stars that died before the sun was born. And one day, in the unimaginably distant future, the atoms that are briefly, you will be part of whatever comes next. There is no sharp line between you and the cosmos. There is only borrowing and giving back and borrowing again, an endless slow exchange of the same ancient material passing through one form after another, like water moving through clouds and rivers and seas and rain, never used up, only ever on loan. And so, even now, even in your dark and quiet room, you are part of that exchange. The warmth you feel under your blanket is, at its root, starlight. The energy that keeps your body warm came from the sun, which is a star, fusing hydrogen the way the first stars did, pouring out light that crossed 93 million miles of space to reach the earth and grow the food that became the warmth in your body tonight. The breath moving in and out of you carries oxygen made inside ancient stars. The iron carrying that oxygen through your blood was forged in a stellar core and scattered by an explosion before the sun existed. You are not watching the universe from the outside. You are one of its quiet, temporary, miraculous arrangements, lying still in the dark, made entirely of its oldest material, briefly aware of itself. There is one more small comfort I want to leave you with before the story fully winds down, and it is this. For all the immensity we have walked through tonight, all the billions of years and the trillions of galaxies and the unthinkable spans of the deep future, the thing that matters most in the whole story is happening in small, warm, ordinary places, exactly like the one you're in right now. The universe spent nearly 14 billion years and built 100 billion galaxies and forged the elements in the hearts of dying stars. And it produced, among everything else, the simple ability of a creature to lie down at the end of a day, in a quiet room, under a roof, and rest. That, too, is part of what all of it was for, if it was for anything. The grand story does not happen only out there, in the blazing cores of stars and the depths of the cosmic web. It happens here, too, in the slow rise and fall of your own breathing, which is itself a small piece of the universe, keeping its quiet rhythm in the dark. There is a question you might have been quietly turning over this whole time, and it is a fair one. So let me answer it slowly before we wind down. We keep saying the universe is about 13.8 billion years old, with a confidence that might seem almost suspicious. How could anyone possibly know that, to within a few percent, for an event no one witnessed? It is a reasonable thing to wonder. And the answer is one of the most satisfying parts of the whole story, because the number does not rest on a single measurement that we are simply trusting. It rests on several completely different methods, looked at by different people using different instruments and different reasoning, all arriving at very nearly the same answer. When independent roads lead to the same place, you begin to trust the destination. Here is the first road. We can measure how fast the universe is expanding today by watching how quickly distant galaxies are receding. If you know the present rate of expansion, you can, with care, run the expansion backward and estimate how long ago everything would have been together. That calculation, refined over many decades since Hubble's first rough attempt, gives an age of roughly 14 billion years. That is one road, walked by measuring the motion of galaxies. Here is a second, completely separate road. We can look at the oldest stars we can find, the ancient, slow-burning stars in the dense clusters that formed very early in the galaxy's history. By understanding how stars age, how quickly they burn through their fuel, we can estimate how old those oldest stars are. And the answer comes back as something over 13 billion years. Now, here is what makes that satisfying. The universe must, of course, be older than the oldest stars inside it. A container cannot be younger than what it holds. So the age of the oldest stars sets a floor, and that floor sits comfortably just below the age we got from the expansion. The two numbers do not contradict each other. They fit together, like a lid settling onto a jar. And here is a third road, the most precise of all, and it comes from that ancient afterglow we have talked about so much, the cosmic microwave background. The faint ripples in that ancient light, mapped in exquisite detail by the satellites, carry within them a kind of fingerprint of the early universe, the precise mixture of ordinary matter and dark energy, the exact geometry of space. From that fingerprint, physicists can calculate the age of the universe with remarkable precision, and the number they get is 13.8 billion years, give or take only a little. 3 roads, the motion of galaxies, the age of the oldest stars, the fingerprint in the ancient light. All 3 converging on the same answer, arrived at by different people through entirely different means. That convergence is why we can say the number with a calm and quiet confidence. Not because we are certain in the way a person is certain of something they wish to believe, but because the universe keeps telling us the same thing in 3 different languages, and the translations agree. I find that deeply reassuring, in a way that goes beyond the particular number. It is a reminder that this whole towering story, strange as it is, was not invented or imagined or hoped into being. It was measured, checked, doubted, and checked again. Every claim we have made tonight has been tested against the stubborn evidence of the actual sky. And only the claims that survived the testing made it into the story. That is what gives it its weight. We are not telling you a myth about the beginning of the world. We are telling you the slow, hard-won findings of generations of careful people who insisted on letting the universe correct them whenever they were wrong, and who were wrong often, and who kept going anyway until the picture came clear. Let me give you one last true thing to hold, and it is one of my favorites, because it brings the very beginning of the universe right into the room with you. Remember the cosmic microwave background, the afterglow released when the fog lifted, the oldest light there is, still arriving from every direction in the sky. For most of human history, that light was completely undetectable, far too faint and too cold for any eye. But here is the lovely part. If you are old enough to remember the days of analog television, the kind with an antenna, you will remember that when a channel had no signal, the screen filled with a snowstorm of static, a hissing flicker of random dots, and the speaker poured out a soft, formless hiss. A small fraction of that static, a small part of that snow, was the cosmic microwave background. The faint afterglow of the universe's first light, after traveling for almost 14 billion years, was landing on the antenna and showing up as a few flecks of snow on the screen. The beginning of everything was quietly playing on the television, in the empty channels, in living rooms all over the world, and almost no one knew they were watching the oldest thing in existence. I find something deeply peaceful in that. The grandest event imaginable, the birth and unfolding of the entire cosmos, did not stay locked away in distant abstraction. Its echo was in the ordinary rooms of ordinary houses, in the soft hiss between stations, gentle and constant and easy to overlook. The universe is not somewhere else. It is not a place you have to travel to. It is here, all the way down, in the warmth of your blanket and the breath in your chest and the faint, ancient glow that has been falling on every roof, including yours, every second of your life, whether you noticed it or not. You have been bathed in the light of the beginning since the day you were born. You are bathing in it right now. So let the bigness of it settle into something soft. There is a particular quality to the deep universe that I think is worth borrowing as you drift towards sleep, and that is its patience. Nothing out there is in a hurry. Gravity took hundreds of millions of years to gather the first stars, and it did not rush. The stars take billions of years to live their lives, fusing one atom at a time, in no particular hurry to finish. The galaxies drift apart over spans so long that a human lifetime, by comparison, is less than the flicker of a single moment. The whole cosmos operates at a pace so slow and so steady that it makes the worries of a single day, the things that turned over in your mind earlier, seem to soften and recede. The universe has been patiently becoming itself for 14 billion years, and it will go on patiently becoming itself for far longer than that. And somehow, knowing that, the small, urgent things can loosen their grip a little. You do not have to solve anything tonight. You do not have to finish anything. The cosmos certainly is not finished, and it rests easy. Think of how much quiet there is out there. Between the stars, space is almost perfectly empty and almost perfectly silent, because sound needs air to travel, and there is no air in the gulfs between the stars. The vast majority of the universe is profound, undisturbed stillness, cold and dark and serene, with the occasional island of light drifting through it. We tend to picture space as dramatic, full of explosions and collisions, and those things do happen. But they are rare sparks in an ocean of calm. For the most part, The universe is the quietest place there is, a deep and abiding stillness stretching out in every direction, patient and unbothered, keeping its own slow time. There is a kind of permission in that stillness, an invitation to let your own mind grow quiet and unhurried to match it. And as your thoughts begin to slow, you might let them wander, gently, back through the story one more time, not to study it, just to let the images drift by like scenery from a slow train at night. The point smaller than an atom, holding everything, the sudden silent unfolding, the cooling glow fading from white toward red, the long dark with gravity working unseen. The first star catching light in the blackness, and then another and another, until the dark fills with scattered fires. The giant stars living their brief, brilliant lives and dying in light brighter than whole galaxies, casting their forged elements out into the dark like a sour scattering seed. New stars forming from the ashes of the old. Galaxies turning slowly, vast and patient, strung along the invisible web. A small cloud collapsing in one ordinary corner, lighting a new yellow star, and around it, worlds gathering out of dust. One blue world, warm and wet, where the stardust learned to copy itself and grow, and eventually to look up. And the long road forward into the deep quiet, so far away that we are still standing in the early morning light. You do not need to hold any of it. You can let each image come, and then let it go, the way you let go of the day. The universe does not ask you to remember it. It only made you, briefly, out of its oldest material, and gave you, for a little while, the strange and lovely gift of being aware. That awareness can rest now. It has done enough wondering for one day. So let your attention come back, slowly, from the depths of space, back across all those billions of light years, back past the galaxies and the stars, back to our own quiet sun, back to this small world turning gently through the night, back to the country you are in, the city, the building, the room, back to the bed, or the sofa, or wherever you have settled. Back to the weight of your own body, resting wherever it is resting, held by the same gravity that built the stars. Feel that weight for a moment. The gentle pull that has been with you your whole life. The same force that gathered the first galaxies out of the dark. Now doing nothing more dramatic than holding you softly against the place where you lie. Let your breathing slow now, if it has not already. There is no need to make it slow. Just notice it. The quiet rise and the quiet fall. The air moving in and the air moving out. Carrying with it those ancient atoms of oxygen, forged in the hearts of stars that died before our sun was born, passing through you for a little while before moving on. Each breath is a small piece of the cosmos doing exactly what it has always done. Moving, exchanging, continuing. You do not have to manage it. It happens on its own, the way the stars shine on their own, the way the galaxies turn on their own, the way the whole great machinery of the universe keeps its slow rhythm without anyone watching over it. Your breath is part of that same rhythm now, and you can let it carry you down. Notice how the room holds you. Notice the soft dark and the quiet, and the gentle weight of the blanket if there is one, and the way the surface beneath you takes your weight completely. So there is nothing you need to hold up, nothing you need to brace against. You can let your muscles forget their work, one part at a time. Let your jaw unclench. Let your shoulders settle down away from your ears. Let your hands grow heavy and loose. Let the long muscles of your back and your legs give up their holding and sink. There is nowhere to be. There is nothing to do. The universe will keep unfolding without your help tonight, exactly as it has for 14 billion years, and it does not need you to stay awake for it. And if your mind wanders back out, up through the roof, out past the moon and the sun and the nearer stars, out among the slow-turning galaxies and the invisible web and the patient dark, that is all right. Let it wander. Space is a quiet place to let the mind drift. It is mostly stillness out there, mostly silence, mostly the calm, cold dark, with islands of light scattered far apart. And there is room in it for any thought to grow small and quiet and finally dissolve. Whatever was loud in your day can grow quiet against the size of all that. Whatever felt urgent can soften. You are a small, warm point of awareness lying in the dark on a small blue world, made of the oldest material there is, and for tonight, that is more than enough. That is, in fact, almost everything. The people who pieced this story together are mostly gone now, or will be one day, like the stars they studied. Lemaitre, the quiet priest who first dared to say the universe had a beginning. Hubble on his cold mountain, watching the galaxies flee. Cecilia Payne, reading hydrogen in the light and being told to doubt it. Penzias and Wilson, cleaning their antenna, listening to the oldest sound there is without knowing what it was. Vera Rubin, finding the invisible matter that holds the galaxies together. They did their work, one careful piece at a time, and they handed it on. And now it belongs to all of us, including you, lying here in the dark, holding the whole shape of it for a moment before you let it go. They would not mind you falling asleep inside their life's work. That is, in a way, the gentlest thing you could do with it. So let it go now. Let the story settle and fade, the way the first light faded into the long afterglow, the way the stars will one day fade into the long quiet. There is no sadness in that fading. It is just rest, the deepest and most natural thing there is. The thing the whole universe is slowly, patiently moving towards across the unimaginable ages. The stars rest, the galaxies rest. The cosmos itself is winding down across spans of time too long to feel, toward a great and gentle stillness. And tonight, in your own small way, in your own quiet room, you get to do the same thing, far sooner and far easier, simply by letting your breathing slow and your thoughts grow soft and your body grow heavy against the dark. You are made of stars. You are lying on a fragment of the universe that gathered itself together and woke up and learned its own history. And now that small piece of the cosmos is allowed to rest. Let your eyes stay closed. Let the dark be soft. Let the faint old light that has been falling on your roof your whole life keep falling, quiet and constant while you drift. There is nothing left to understand tonight. There is only the slow rise and fall of your breathing, and the gentle weight of you against the world, and the long, patient, peaceful turning of everything, carrying you softly down into sleep. Rest now. The universe will keep its own slow time, the way it always has, and the way it always will, long after this quiet night has passed. And you can let yourself fall, gently, all the way down, into the dark, into the warmth, into sleep.